So O base is 2. I need to set I base to 2. We're using the BC command from the Linux prompt after you've logged into the Jupyter Hub. If you're at home, you will use jmkll.org and it should work. It did this morning. So if I say ibase equal to 2, so both my input and my output is going to be binary. So let's take our 42, which is, we'll say 1, 0, 1, 0, 1, 0. And I want to add 0, 0, 0, 1, 1. So I'm using, well, I don't need it. It assumes I will use the same number of bits. And then remember 1 bit, a single binary 1. 4 is a nibble, 8 is a byte. Okay, so we have, and we'll be using 8 tonight because I want to show you how this applies to your IP addresses and a broadcast and a net mask. Okay, and how that processes using binary arithmetic. Okay, all right. So now if I hit enter, there's my new answer. Now, how do we convert binary and decimal? Well, there's an algorithmic way to show you this. And then there's just a simple math way to do so. And I teach the simple math way because it's easier to learn, and then you can learn the more complex way later on. Okay. All right. Now, how does this work? How many have taken the quiz in Canvas, the binary decimal hexamal thing? Yeah, pretty easy, isn't it? I give it to every single class. So just keep the answers, and it's pretty much the same thing. But what you're doing is learning how to convert binary to decimal. So what I'm going to do is go into Canvas here and bring that up so you can see it. I've got it in there somewhere. And I'll go into the assembler class. Here we go. All right, assignments, binary hexadecimal. There's a YouTube video, and then I'll open this one. A little hard to see, but basically, what is the most significant bit in base 10? The number on your right or the number on the left? The one that has the most value. Left. That's the same way in binary. Left is your most significant bit. Now, we can go way beyond 8 bits, okay? And 64-bit registers and all that stuff. Well, here's how it works. This is the easy way to do it. When you have a binary number, you just look at this pattern. 1, 2, 4, 8, 16, 32, 64, 128. If I add another bit and I put a 1 there, what's it going to be worth? Bingo! You get it. So what you're going to do here is simply, okay, I've got 128 plus 32 plus 8 plus 4 is equal to 172 on an 8-bit system. Now, why am I using 8 bits? Your IP address. Okay. Now, I will do this on Windows to show it to you. It's in Windows, it's IP config. On your machines in front of you, on Linux, it's IF config. That is basically 8 bits, dot 8 bits, dot 8 bits, dot 8 bits. This is your IP version 4 address. This is your IP version 6 address. This is in hexadecimal. This is a decimal.
Are you able to read IPv6 addresses and immediately identify the classes like IPv4s yet?
They're classless.
I meant, like, for example, like the FE080, certain ones are local, certain ones are what's the one router? Are you able to do that like with IPv4? Like if I told you
IPv4, yes, you have private network addresses. IP version 6, the answer is no. There is no private because everything can have its own address because there's enough for like for every there's so many addresses.
no, there was what is it called? I call it Slack. I don't
You
know
can't.
But there's you know how like when Windows fails, it goes to 169 something, and you immediately know that.
Oh yeah, that's the APIPA address.
Yeah, but yeah. You notice how you identified it? Are you what I'm getting at is how long, or what my question was how long did it take you to get familiar enough where you could just look at an IPv6 address and immediately identify it?
I don't use IPv6, so I haven't learned how to do that yet. Oh. Okay. Most of the people I know, I asked if they're going to move to IP6 here. They said no. Because as the rest of the world moves to IP6, there's more IP4 addresses that we get to reuse. So I talked to the fellow taking care of Foster Farms. He was their chief network admin, and he was getting bored. He was about ready to retire. He says, I think I'm going to convert the enterprise to IP6 because he was bored. Now, it brings some nice things to the table. It's a lot less chatty. It's a lot less noisy on the network. But again, it's just ones and zeros and a whole lot of them. Okay. And the reason I'm showing you 8 bits is so you can see that, oh, look, our subnet mask is 255.255.255.0. What's 255 decimal in 8 bits? So let's go back to our little screen here. So what we're doing is I show you a very simple way to do this. And you basically, now let's say 255, I can say, add it all together and say, okay, what's 1 plus 2 plus 4 plus 8, blah, 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 blah. That's 255. It's all 1. And when we represent this in hex, it's FF. So our broadcast is all 1s. Now this is how we get, or the net mask is all 1s. And that is how we use our binary. We AND it basically to get the broadcast address. And I'll show you how to do that as we move on in class. Okay. So this could be all zeros, that'd be 0. This would be all zeros, there's a 1. 255 is all 1s. FF. 254 is all 1s except that one. FE. This is not hard. But understanding this binary thing and why there. Now, what I did down here, this is binary to decimal based on the value. Most of the numbers that you see on disk or in embedded code are in hexadecimal. Okay. And it represents a binary number somewhere. So you're not technically converting between bases. It's in binary, and you're taking groups of 4 and putting a hexadecimal number on it because it's easier to read. Does anybody really want to read a string of 64 bits? Well, that's kind of hard to see. Okay, it's really hard to read. So down here, we get our binary first, and then we say 1, 2, 4, 8. When we add all those together, we get to, what do we get? 15, right? And what is hexadecimal? That's 0 through F. We talked about that last week, right? Ancient history. All right. So we'll be playing more with this as we move on. So to convert these, we take this one. That would be 1. F. So that would be 1F in hexadecimal. And then we add up the numbers, see what that is. Okay. That's all there is to doing this basic quiz that I put out there for you. Okay. So going back to our addition, where we added these two together, how does this binary add work? Okay. Well, this is where I need to go to the board, I guess. And we'll do a quick binary add here. And then I'll have to do the stop share, I guess. And over here. Oh, all right. Hopefully you can see this on, so I don't have the chat up. Okay. So I have one student online. So if you can't see this, let me know somehow. Okay. Let me find a black pen. All right. Now, let's take what we just did, but let's make it 8 bits because we're going to do this 8-bit thing with networking. I'm going to show you why we kind of need to know how to do this. Okay. So I used 01, 01. That's 0. And then I need 1, 2, 3, 4, 1, 2, 3, 4. Okay. So I'm using 8 bits and I'm using the leading zeros just to make it a little easier. Okay. And then I added basically this number to it. Okay. We got to carry bits, right? This is kind of how things work. We have 1 plus 1. We can't say 2. We have to carry. So 0 and 1 is a 1. And then we say 1 and 1 is a, oh, it's 2, but I can't write 2. So I do a 1 and then I carry, bring it down, bring it down, bring it down. Whoops, that's a 0, 1, 0, 0. And that's the same answer that I got here. Right? Other than I put leading zeros here, but I didn't put there, right? Or not? No.
Almost.
Oh, I wrote down the number different, didn't I?
The second one.
Yeah. 1, 1, and oh, I forgot. 1. Oh, 0 in a carry. That's right. 1 and 1 is because you can get a carry. Like, for example, let's say this is the 1. 1 and 1 is going to give me a carry. Now I have 3 1s. Now what do I do? Well, I say 1 here and then I have to carry 1. A little confusing, I know. This is why we're using a tool.
So is it essentially the 2 1s cancel each other out? So if you have a 1 and a 1, it becomes a 0,
and then you carry it. Yeah, that's exactly what's happening. Okay, so think of the numbers like 10 and 20. Think of the bases you're familiar with. The part that I want to show is as we have some fun with our binary here, and that's why I did it first, because you teach this once a semester. Guess what? My brain leaks. I forget things. So remember, I'm not the expert. We're kind of all on this together.
Am I jumping ahead if I ask the far left numbers be changed to 1 and a 1? Or is it jumping ahead? You're going to get to that.
That would carry over into another register. And that in what we are learning in this beginning part is we're not going to worry about that yet. But we will be doing something called shifting. And this is where binary math gets really slick. If I want to multiply by 2, all I do is shift all the numbers and everything's multiplied. If I want to divide by 2, I shift. Shift right, shift left, boom. So it's very fast that way. And then next week, we'll get into what the gates look like, an AND gate, NOR gate, XOR, and build our own little adder so we can see how the truth tables work with binaries, ones and zeros, and see how it kind of fits together. Okay. You're not in 30 plus years out there in industry, I never did much of this, but in networking, you learn how to subnet in your head because you're anding the broadcast off the IP address. So you know what your address space is, because you don't want too many hosts on your subnet where it's going to get really slow. Okay. So that's what we'll finish out with tonight. Okay. All right. So now let's do a couple more of these and have some fun. All right. Now there's no clear screen per se. So what I'm going to do to get out of this, you just type in quit, and I'll type in the word clear, and it clears the screen. Now I'm going to go back to my screen share. I know I'm going to forget to do this. All right. And hit share. I'm going to pop into another tool real quick so I can make the screen much larger. I'll still go to the same machine. And I'll make this quite large. See, control. What is it? It's this one. Oops, magnifier. That's what you want. Let's see. Is that going to work for me here? Oh. Oh, it's not working. It worked early. Oh, there it is. It's control plus sign. Using Moab Extra. Everybody's different. Isn't that fun? All right. That's kind of annoying. Let's get rid of that. So I can type. To get out of Unix tools, you're either going to type in quit or exit or control D. Okay. Clear. Ignite will do. I think it's B or Q. Yeah, Q. BC minus Q turns off that warranty thing. Okay. Doesn't change anything else. It just turns off the warranty. So your screen's less noisy. Okay. So, but it always defaults to base 10. So we want to use our O base, right? So we'll change our O base. O base is equal to 2. I base is equal to 2. And now let's use an 8-bit, and we'll play with it for a second here. We'll use 1, 2, 3, 4, 6, 7, 8. Okay. Now, I'm curious to see what that number is. So let me assign that number. I can use the up arrow key, hit home, and say A is equal to that binary number. And then if I type in the letter A, now what happens if I change my O base? O base, let's go with 10. A, it didn't work. That's because I have to input and output. Oh, well. Never mind. We'll come back to that. Let's add some numbers. So I'm going to put something into B. And I will say 0, 0, 0, 0, and then 1s. Now, what do we want to do with these in binary? We can add them, we can subtract them, we can multiply them, and we can divide them. But let's stick with taking these two numbers and add them, and then we'll subtract them, and then we will multiply them. And we're going to look at the results, and then we're going to figure out what's actually going on using some scribbles on the board. And will I get lost? Yes, I will probably get lost. Okay. So let's say A plus B. And now we're going to assign this to a new variable name. We'll call this sum. sum is equal to, well, I better put a number on it just in case it's a keyword. So sum 1 is that. That's what the numbers are. But I still have a value in A and I still have a value in B. So now let's subtract them and call it sub 1. So sub 1 equals A minus B. Oops, 1. And do sub 1. That's what it looks like when it's subtracted. And you're like, I don't get it. That's okay. I don't either. We're going to play with this and I'll show you how to use this in binary. Okay, we'll do the subtraction on the board. And now we're going to do the multiplication. So let's take, and we'll call this mul 1 is equal to A. Well, I think that's the multiplier. How many? Quiz! What's that?
Delta.
Exponentiation. In which languages?
C.
C, C++. Is it that in Python? No. In Python, it's this. So exponentiation is something you always have to check on because that is a bitwise operator in Python. It moves things by 1 bit. And I believe this is a bitwise operator in BC. So we're going to find out. Okay, so we'll say A times B and then do mul 1. Wow, that was cool. All right. Because it's, oh, that's why. You can't use O base to convert the value. You actually have to change O base and then redo the value. Okay. Okay. So we've just done some addition and subtraction and multiplication in binary 1s and 0s. Okay. Now let's play with them a little bit on the board and tinker with it. And I have a book that I will put on the website, you know, this one. I have a book that goes over all this, and all the stuff for this semester is going to be free because it doesn't move around much. Okay. All right. It's all been the same. And Boolean algebra we'll probably get to the week after next. Okay. And then I have a whole mess of stuff on assemblers. Okay. All kinds of fun stuff. All right. And there is a lot of good references for doing binary math. Just search on how do I do binary multiplication? And it will walk you through the entire process. Binary subtraction is a pain. But what the quick thing you do is you just change all the 0 to 1s. You just, it's called 2's complement. Or you just invert it and then add. So everything is addition for the most part in binary because it's so fast. And we talked last week that even the cheapest 4-function calculators that came out many years ago have a square root. Well, doing square root in binary is pretty easy. Find the number of bits, shift it over that many bits, and there's your answer. Okay. All right. So now let's play with, where would my terminal? Oh, yeah, it went down here. Here. Okay. So let's start with our addition and stop share so the board shows up. All right. So we had 1, 2, 3, 4, 5, 6, 7, 8, right? And then I did 1, 2, 3, 4, 1, 2, 3, 4. Now we're going to add. Okay. Now let's see if we can do it better today. Okay. 0 and 1 is 1. 0 and 1 is 1. 1 and 1 is a 0 with carry. Now we have 3 of them. So we have a 1 and a carry. That kind of makes sense a little bit. Okay. So now I have the same thing. A 1 and a 1 is a 0, right? With no carry. Or does it? Yeah, one. My brain is, yeah, with a carry. And then we have our 9th bit over here. Okay. So you would just move it over one more, but we're going to stick with 8. We're going to use 8 bits because I want to show you what happens with our IP addresses. Okay. Now let's look at the subtraction. So that was addition. Okay. Now it's just like in where you want to be able to, well, I can't subtract a 1 from a 0. So what do I need to do? Borrow, right? I got to borrow. So I got to move all this stuff over. So this becomes a 0, this becomes a 1. Then I got to borrow. This becomes a 0, borrow, borrow, borrow. You can see how complex all that gets. Yeah. Oh, I'm so confused. All right. Now, let's leave it that way. Let's try something. Okay. You heard me mention 2's complement, right? So let's use a different color pen here and have some fun with this. I'm going to write my original number over here. Now I'm just going to do a straight inversion. So wherever it was a 1, I'm going to put 0. So I'm going to say 1, 1, 1, 1, 0, 0, 0, 0. Now, what happens when I add these numbers? I got a 0, 0, 1, 1. We have a 0 with a carry. We have a 1 with a carry, a 1 with a carry, a 1 with a carry with the extra 1. Now, let's look at that pattern. What's it look like? Close. Did I get it right? No, I missed one. 1, 1, 1, 0. Because when you do your flip, they call it 2's complement. They invert them, add 1. So you invert them like this, and then you flip. Okay. And that's kind of what the 2's complement's about. We'll talk more about that in a bit. But you can see that playing around with flipping this one way or the other makes things pretty darn easy. Okay. So let's go back to our original number and experiment. I think it's more fun to learn this kind of stuff this way, where you poke on it, break it, and oh, that didn't work. I'm not even close to the right answer. Why not? I have no idea. Let's figure it out. But as you ramble around and you poke on things like this, you're finding you're developing a much bigger repertoire of how things work. And learning how to troubleshoot is not easy. Okay, now let's take this same number that we just did, and we're going to move it to the left by 1. Okay, so basically we're going to write the same number, but we're going to put a 0 at the end of it. Okay. And then let's add it together. 0, 1, 0, carry, 1, carry, 1, carry, 1, 1. And then this is a 1, that's a 1. Okay. And now we have 8, right? So we now have 1, 1, 0, 1, 0. So it's, oh, it's so close. Almost looks like subtraction, doesn't it? That's a shift. Okay. Cool. All right, Chris, what am I doing wrong? Two's complement, you swap and flip 1, right?
I can't see it from here.
Oh, okay. But two's complement, you take you basically you flip them all and then you add 1. And we did that, and we came up with a number that was it this one? It was that number, right? I don't remember. Yeah. Okay.
So you're trying to get the difference, correct?
Pardon?
You're trying to get the difference?
Yeah, we're seeing what we can do, what cheater method we could do to create subtraction.
Yeah, okay.
That's what we're trying to do. Because we can do subtraction by carry, borrow, borrow, move, move, move. Okay. All right. So what we've done so far is we've flipped them all and we added them. Then we flipped them all and added 1 and then added them. We've shifted them one way, added them. Now we'll do shift the other way and add them. Okay. Just to see what we can come up with, see what kind of numbers we get. Okay. But then the question I have is, oh no, our number was this. Well, 4 of them. And when I shift, what happens to the 1? Does it go off into space? Do we lose data? No, it just gets stored somewhere. Okay. And negative numbers and all that fun stuff. Okay. So, but for the sake of argument, we're going to lose some data. Okay. Oh no, I've just lost some data. And I'm going to bring in, and then I'll add this together and see what we come up with. All right. So now it's basically 1 and 1 and 0 with the carry.
If you are willing to accept the Church of AI, they have a step-by-step.
Yeah, I know. I know. We have all this stuff. You can go find all this stuff, but we're having some fun with this right now, because where I want to show you, you're never going to do binary math in your head unless you go into networking and do subnets on IP4 addresses. That's what I'm getting to in this. Okay. So we're just kind of having some fun with this, these numbers. Okay. All right. 0, 0, 1, 0, 1. So that doesn't look like anything up there, does it? Because we didn't try a divide. I wonder what a divide would look like. That'd probably be terrible. Let's do get 1. Well, part of it. Cool. All right. Now, on the Unix box, let me exit here.
You can have remainders in binary division?
Yeah, you can do binary division, but it doesn't.
No, it's I typed it in the AI thing and it said you can get a remainder. I didn't know you can get a remainder.
Oh, yeah, I do want to talk about modulo and the difference between modulo and remainder.
Oh,
how that, but right now I want to do this because I want to get this so I quit talking about it. Oh, that's too big. All right. I want you to notice this number here and that number there. and then this number here. Okay. So I have an IP address, I have a net mask, and I have a what they call broadcast. This binary stuff that we're talking about applies to you in the world of networking like so. Okay. All right. Now, remember I said the 10 dot is 8 bits. The 18 dot is 8 bits. 171 is 8 bits. And 11 is 8 bits. So let's convert that 1018, 171, 11 into binary, just like on the quiz. Okay. And I don't have screen share. That's okay. All right. So I want 10 in decimal. So I need an 8 and a 2. And this is my dot. Okay. So now I have 18. So what numbers do I need if this is, you know, the 1, 2, 4, 8, 16, 32, 64, 128. This algebraically, it's 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, so on. Okay. I just wrote it that way. So you can, wherever there's 1, add that number. Okay. Makes it easy to convert. So I need 18. So how about 16 and 2? Does that give me 18? Yeah, I think so. The last time I did math, which was what? 2 seconds ago. 0. And then I need a 0. And help me, I probably make a mistake. 0. And dot. And now I need 171. Okay. And I think I have that up here somewhere. Oh, look. I have 170 already written out. What do I got to do?
Add a 1.
Add a 1. That's not too hard. So I'll do 1, 0. What do I got there? 1, 0.
10, 10, 10.
Yeah, there we go. 1, 1. And then the last one is 11, which is going to be 0, 0, 0, 0, 8, and 2, and 3. All right. How this applies to you. When somebody says an IP address, that's what we need to get on the internet. Right? DHCP, Dynamic Host Control Protocol. Say it with me. Dynamic Host Control Protocol. All these buzzwords that we get to learn about. Okay. So we now have a net mask that is written like this. And then 8 zeros. 4, 5, 6, 8. Okay. They're supposed to be lined up. How many ones are there? 3 times 8 is. When you're in networking, you would write this address. I use a different color, 10, just so you can get an idea here. So it's 10.18.171. And you put a 0 here. A 0 on either end of an IP address is invalid and wrong. /24. That means there's 24 bits in the net mask.
Can you put a 0 intentionally to disconnect the machine in a hurry?
It won't work.
It won't let you set it?
It won't work.
No.
You can try it. Give yourself a fixed IP address and try to connect to another one with a 0 on it.
No, I'm not trying to connect. Like, say, for example, like, say you screwed up something and you need to disconnect immediately. Can you put a 0 to stop something on your own machine?
No, technically, no, because your IP address is bound to your MAC address. And in order to release the IP address from the hardware address, in Windows, you would use IP release renew, or you would release it to the DHCP and then renew it. But if you forced it, arc poisoning or something, it's not going to route. It's not going to work. It's not going to talk.
But that's what I want it to.
It would be like unplugging the cable.
Say, for example, like I'm on a guest computer at school. I don't have permission to change the firewall, but I want it to stop network traffic. Would that work? Like assign my own IP address with 0?
No. What he's trying to ask is, if a network is running and I need to immediately stop my machine from sending or receiving data, what can I do? The easiest would be unplug it. But from a software side, you're going to need the admin rights to drop the drivers. And you're not going to get that in a classroom box. Okay. Because you have to be an admin to bring the interface down and then back up. Okay. So now I have this another funny looking address that I just had on the screen here. This one. How did that come about? Can you kind of see that, Chris, or did we have a?
No.
You can see that one? Okay. All right. How did that and that give me this? Andy. Okay. So the way this works is wherever there's a 1, it just passes the 1 down. Okay. So 1 and 1 is still a 1. And 0 and 1 is still a 0. And this is our first truth table that we are going to be building today as we build on this binary stuff that we play with. Okay. All right. So let's go. We got all these 1s. And then what happens is now these are all 0s. And the way the AND truth table works is if I have a 1, it's a 0. If I have a 0, excuse me, the other way around. If it's a 1, it's a 1. If it's a 0, it's a 1. So anything is going to give me a 1. So my AND truth table is going to give me this. Here. And these are basically going to just pass through. Make sure I'm getting them all lined up right with all the appropriate 0s. All right, that's going to be 1, 0, 1, 0, 1, 0, 1, 1. Now, we take these and convert them back into decimal. What do we get? 10.18.171.255. Now, why does this mean anything? This tells me that the subnet is 24 bits, net mask. That means I can have that many unique addresses. I can go from 10.18.171.1 to 10.18.171.254. Okay. So I can have 255 minus 2, basically, 253 addresses on a subnet. So I can put 253 machines on a net mask of 255, 255, 255. Or if you're a NetBSD person, FFFFF. Okay. Now, yes.
So the second binary number there is the subnet mask. And
the subnet mask, this one here, that's this is the mask,
right?
And this is the broadcast that says, hey, I'm on the network.
And the binary number there.
Yeah.
111.
This is the net mask.
That's the subnet mask. So the one above that, what do we call that?
That's the actual IP address. That's this guy.
Okay.
So somebody says, here's an IP address. Let's say it's this one. And I'm going to pick, I have a subnet mask that is 24. That tells me how many bits are in my net mask. And then I can find out what my ranges are on that. Most of our home routers are using 192, 168, 1 dot from 100 to whatever, right? Long reasons why we're using 10.
But then, so what's the third binary number that on the whiteboard?
Yeah, this one here. What is that?
Yeah.
That is the broadcast.
Oh, that's the broadcast. Okay.
The
Great.
broadcast. The broadcast says, "Hey, I'm here," but the broadcast only works on that subnet. Now, what happens when I change this number to a different number besides 24? It's going to change my broadcast and change the number of hosts underneath my subnet. Okay. Why do I need binary?
Now it's done.
Networking. That's binary. Okay. So let's just make it kind of not too hard. Let's just say our net mask is 25. Well, that's not technically right because it has to be in order. So we need to put a 1 here. So what's that number going to be if I have a single digit number there?
128.
128. So if my net mask is 25, my net mask is 255, 255, 255, 128. And then my broadcast turns into 128. Okay. Well, let's do it. Okay. So we're going to add a 1. Okay. And then basically it turns into this. So it's not 128. I'll take that back. So it's going, so if I do this in my head, I've got 10, got 18, 171. What's that number? 128 flipped, add them all together, 127. So my broadcast is 127, and this allows me a fewer amount of hosts on my subnet. Okay. This is practical binary. You use it every day, whether you know it or not. Okay. This is your IP address, your broadcast, your subnets, and networking 101. Okay. How it applies to you. All right. Now that we're all confused, let's talk about this ANDing truth table. Okay. And let's start. I'll just look it up on my good friend Google here. I'll go back to my screen share. I have, or maybe I was on screen share. Oh, well. Sorry about that. All right, go down here. Now there's a gazillion things on this. Let's say truth tables. And for the sake of argument, I will use logic. This is part of the reason. Notice how it's written. P and then the prime P, T, true, false. This is why logic and discrete structure is required for computer science. You're learning logic. And what is logic? Well, it's 1s and 0s, basically. And you're creating truth tables. Okay. So, and the way you write this, this table, if P is true, its negation is false. All right. Oh my gosh. How many have had logic? Okay. Does this look familiar as far as what are the numbers on up and down mean? Yeah. Well, I've forgotten it all. So you're going to have to help me remember. Okay. All right. So what I'm going to do now is go back and say truth tables logic and use this word Boolean. And let's take that one. This is what I'm more familiar with, is the A's and B. This is Boolean algebra. There's an entire system of algebra for binary. It's really kind of fun because this is how you design chips. I have 8 bits and I'm going to do some adding. So what bits do I need to do to make an adder add? Next week, Tuesday. And I'll promise I'll have it working in my brain a little better. Okay. All right. All right. So here's a truth table. Inputs, off, off is off, on is 1, on. And therefore, this is our AND gate truth table. Notice how it's shaped. This means something. This is an AND. And the way I remember it is 0 and 0 is always going to be a 0. A 0 and a 1 is a 0. A 1 and a 0 is 0. A 1 and a 1 is 1. What did we get over here? We got the ones when we had a 1. Only when it was a 1 and a 1 did we get a 1. This is why our broadcast looks almost like our address. Okay. Make sense? Kind of, sort of? Not? Maybe. So this is a truth table, and I have 2 inputs. And remember, inside 273, if I go to, and you go to that lovely picture here, it's really hard to see, but that picture is from this guy. His 2-transistor computer. Isn't that cool? That's how he started it. This would be a great way to learn. This is what Steve Wozniak did when he was in high school. He did Boolean algebra and logic gates and built computers for fun on his own. Because it, with only a couple discrete components here, it's not that hard to wrap your brain around this. Yes.
Do you remember a magazine called Make?
A magazine called Make.
Yeah.
Yes, I have a bunch.
Yeah, well, there's an author, I forgot his name now, I had it in my thing. But anyway, he had a walkthrough that builds you up. So you literally start with a 5x5 timer, and at the end result, it's over like 2 books, but it's called Make Electronics. And at the end of that, you learn you're comfortable with a breadboard. And
yeah, Charles somebody.
Yeah, she read it.
Yeah.
That's the book I'm talking about.
Yeah. It's a great book. And it covers a lot of cool stuff.
But the thing you're showing there, that's the second book, Make More Electronics. And so you end with, you start with like random pieces, and at the end, you're
and you just have to know what each one of these little guys do.
He explains it too.
Yeah, and you build a computer, and there's a bunch of things you can do this way. But he's using 2 transistors to create a real computer. You have over a billion in your cell phone. So think of the complexity of the software, and we wonder why things are hard to figure out. Okay. So we have our Boolean algebra. We now have seen a legitimate use for the AND logic in computer science with networking and IP addresses. Your brain hurt?
Never doubted it.
Or is it, hey man, it's cool, I'm gonna go play with this? Let's hope it's the latter, because this is what it's like in this business. You're always learning something new. If you don't learn something new in a day, that day is wasted. Okay. You can learn all kinds of things in a day. And now we have another table. This is a different one. It's called an OR. All right. Here's the symbol. And or, so the way it works here is 0, 0, 0. But when you or it, if you have a 0 or a 1, you're going to get a 1. If you have a 1 or a 0, you're going to get a 1. And then 1, 1, 1, 1. Okay. Here's the Boolean expression. Okay. Down here. Okay. Now, let's say I'm Steve Wozniak and I'm building a computer. And that's really hard to see in the back, but the and is actually written Q equals a little tiny dot D. That's the expression in the little dot between the two, okay, that's the and. And this is an inverter. This is a not. What that does is whenever there's a 0, it flips it to 1. Whenever there's a 1, it flips to 0. This looking familiar if you've had logic? Yep, this is straight out of logic. Now, this is how they write a NAND gate. You can build an entire computer with nothing but NAND gates. Okay. And NAND gates have an interesting logic, is that when you have 2 1s, you end up with a 0. But when you have 2 0s, you have a 1. So basically, that little circle means invert it. So take the AND gate and the truth table that's in the AND gate, and let's reverse the whole thing. So think of the AND gate with the not in front of it on the output, I should say. 2 in, 1 out. That little circle means the not. Okay. And the NOR gate, just like the OR with an OR. And then there is the magic one, exclusive OR. Exclusive OR has saved tons of time in the world of gaming, where you can create shortcuts inside of the game logic by using exclusive OR. Okay. And that's the truth table for it. So kind of what we're going to do next Tuesday is we're going to take a combination of these things and make our own adder. And we'll do it simple. We'll use 4 bits. And we're just going to add, take 2 bits and add another thing together. And we'll scribble it out on the board. And we'll do this. Somewhere, I have a circuit emulator that lets you drag and drop this stuff, and I cannot remember where it is. Okay, I have to go find it.
Are you sure it's circuit emulator? Was it PHET? They had a bunch of those on there.
I can't. I know there's some stuff that's out there. I just can't remember it.
PHET had the electronic simulator, and there's one you could put values in too, if it's just pre-made stuff like that.
Mm-hmm. Now, in the AND gate, is there a limit to the number of inputs you want to put in here? Technically, no. You can have or create an AND gate that has 75 inputs, but the truth table is still going to look the same. Okay. The same with the OR gate. You may have a gazillion inputs, but the truth table is the same. Now, here's where the Boolean algebra comes in trippy. Let's say we've designed our 4-bit adder and it's really inefficient. It uses too much energy. We can use Boolean algebra to reduce the number of gates that are required in the chip or that you need to create circuit. What is the equivalent circuit using Boolean algebra? Now, who's going to use that? Computer engineers, people that are designing chips. If you're writing games, probably not. Or if you're doing databases, probably not. Doing web dev, probably not. But one of the things you could consider, how many like pretty colors on their screens? Yeah, I like pretty colors on the screen. So let's look at the HTML color codes and just take a quick look at them. Notice whoops, let me make it bigger. FF5733. That's in hex. What would it look like if I ANDed those or ORed them or exclusive ORed that number? We'd get the complementary or the tertiary or the quaternary, and I don't remember what the 5 one is, the whatever, whatever. But you can get different color combinations by using this kind of logic against your color. Again, oh, I like the color. Let me put one in. I guess not. Let's do this. There we go. Yeah, here we go. I like this color. C0FFEE. Well, that's a pretty cool color. And then what about this one? I'm not so fond of that one. Okay. So you can have some fun with color codes and then flipping them. What would happen to my color coffee in binary? Now we've learned, now we're going to spend some time with hexadecimal. Most things in computers are stored in hex. So underneath it's all binary. And as they display it to the user, they put it in hex because it's easier for us humans to see that rather than a bunch of these. Right? Now we can convert this into hexadecimal. This would be F00, or in this case, it would be that would be 80. Okay. So if we took the letter C, anybody remember ancient history? How do we count in hexadecimal? What's a 10? A, right? We'll do a quick review on that one. Okay. This is it's all ones and zeros. And hexadecimal. And you notice all the hexadecimal for the IP address version 6, it's all in hex. So still ones and zeros underneath it. It's just hexadecimal. Okay. So when we count in hex, we start with 0 and go to F. And it's basically 1 through 9. And then A, B, C, D, E, F. F is all ones. 9 is what you expect. 1, 0, 0, 1. 10 isn't said, you can't write 10, is 1, 1, 0, 0. So this is your cheater table. So A is a 10. What comes after that?
B.
Yeah, B, and then that's going to be what? 11? Yeah. We still count sequentially. And you can see what's happening here. Now, when I have you write out all the numbers, you're going to see a repeating pattern. And that repeating pattern is, if I continue on here, and then D is, I might get some of these wrong. 1, 1, 1, 0, 0, 1 is, I have 1, 0, 1, 0, 1, 0. Well, I can do that all the way down to 1. The last bit is going to have a pattern of 1, 0, 1, 0, 1, 0, 1, 0. The next bit over is going to have a pattern of 0, 0, 1, 1, 0, 0, 1, 1. Patterns 2 and patterns 4. So you can just kind of memorize that pattern and remember which what. Okay. So if I took the letter C, what do I want to do to it? Shall we AND it? AND it to what? AND it to an F? See what happens. So F is this. And what did we learn about ANDing? What we just did? Ancient history.
Ending anything with a 1 is a 1.
Right. So if we ANDed this, it's still going to end up as a C, which doesn't change anything. Whoops. So that doesn't change anything. Now, what if I did an OR? It would change it, right? And OR, I'll use ones. I'll still use ones. So now I'm going to do an OR. And what's the truth table for an OR? Let's go back here. Oh, where did I put it? Oh, there we go. So an OR, where there's a 0, there's a 0. Wherever there's a single one or a 0, there's a 1. So it looked like this. So what would the color? So when we OR it with F, we end up with an F. So we go to our color code, C. See if it brings it up. Yeah, it does. Oops. One more. There we go. Turns it to an F, fluffy. So you can have some fun with playing with truth tables and see what happens to your color codes. Why not? Apply it. Make something useful. Okay. Now, let's go back to our BC calculator. And BC is not on Windows, sorry. You can get it for Windows. And I want to do BC minus Q for quiet. So now what I want to do is I want to change my base. And we'll do this, some adding and subtracting in hexadecimal. Now let's just do some conversion. So let's say input base equal to 2 and output base is equal to 16. You don't write F because it doesn't know that it's base 16 yet until you hit enter. Now it will go 0 through F. Okay. To go back to decimal, there is no 10. So you have to type in O base equals A to go back to decimal. Okay. So input base 2. It's doing something else. That's not a 12.
I don't think you can set input base before output base. I think you have to do it the other way around.
Oh, you're probably right. Thank you. Don't you love it when your instructor stands in front of you and says, you know what? I didn't freshen up on this. And
all your other examples had O base first.
Oops. We want O base 2, right? Is that what you're saying?
No.
No?
You have to do O base before I base.
If you set
yeah. That makes sense. So we want the input base here equal to 2. Let's give it a value. We'll give it X is equal to, let's go back to our number here, not display X. Now I do O base equals 16.
I don't
and
think
do
so.
X.
No.
Yep.
When you change the input base, it affects everything you type in, including the number that you're assigning to output.
That's true. Yeah, because the 16 is binary, so it doesn't know what to do with it.
Right.
I'll have to read up on that, because if you're in binary,
then you have to.
And if you type in 10, does it get?
It sounds like an AI question.
10,
Go play with it, folks. Let's find out.
If you're in binary and you type in 10, you're setting the output base to 2.
Yes. Yeah.
Yeah.
Yeah. So that's. Yeah, I'm gonna have to play with this. There is now. Let me bring up a few helps that I've played with. There is something called the Linux documentation project.org. And this has been around, it's, state of the art 1996. But this covers things that you will probably never see elsewhere in print. You might see it on Stack Exchange, but there is an entire manual on how to do HTML math c.html and how to do math commands using prime or floating point. And this covers a combination of bash and BC. Okay. How to write an inches calculator. And this is giving you an example of what the actual programming language looks like in BC. It's an interpreted language. You can write an entire mathematical stock forecasting program if you got enough horsepower. Okay. It's not terribly fast because I believe BC is compiled to be single threaded. So it doesn't automatically spawn multiple threads. Okay. But this can go, here's one for does base conversion. Let's take a look at this. Binary, octal. This is a function. It's showing you what it's doing here. You can play with this code, whatever you want to do. There we go, hex. Folks, see that little buzzword there? Here document? That gave me a $25,000 a year raise. Because I used a here document to send all the print streams that people were printing out and hand keying into Excel from the mainframe. And all I did was use a here document, redirected the print stream from the printer to a file and emailed the ASCII file to the user's email box, and they pasted into Excel. They saved tons of money just in paper. Why nobody else thought of it, I don't know. Maybe because, who knows? But anyway, it gave me a nice raise. All right. So here documents are pretty cool. But anyway, off topic. And then there's another one called OPS. OPS. And I'll put these in our little website. Okay, the operators. And this is showing you how division, multiplication. So in BC, remember way back ancient history said, what's the caret? We said it was exponentiation. Oops. What's exponentiation? All right. Oh, I do want to mention modulo. Now, modulo is different than a remainder. And the way I like to describe it is the number of days we have in a year. We got 365, right? Let's say we're at day, I don't know, something or other. 365. And then what I want to do is do this mod 7 thing. Now, what happens when we do mod? It will give us a number from 0 to 6. So we get buckets. Think of these buckets. So if I want to pick a Julian date, and I'll make this easy, I'll say, all right, I'm in the first, or let's say I'm at day 1, modulo 7 is 1, or excuse me, 0. Okay. So it'd be day 0. That'd be Monday. Day 2. What happens is that every time you run a modulo, you're going to end up in one of the boxes of 0 through 6. No matter what number you type in between 0 and 365, it's integer only. A remainder can have a floating point. Modulo does not. So here is an example. How many have seen the Chinese calendar or the Chinese New Year on a Chinese menu? Yeah, you see 12 animals around it, right? And it shows you what years are there. Put the year in, mod 12 it, and it gives you a number that correlates with that animal. That's not too hard, right? I also can show you a personality test. I used to do this in my beginning programming. You take your birthday and you keep adding it up until you get a single number, single digit number. And then you mod that. And then what happens is you get a personality paragraph that tells you what kind of personality you are using modulo. Okay. So modulo has very practical applications, but it's not a remainder. It actually means something different in the world of computers and math. Okay. So think of it as a bucket. And if you have a mod 7, you're going to put thing into 7 bucket. Okay. And if you're going to mod 12, you can pick any year and you're going to put it in one of those 12 buckets. Okay. That's how modulo works. That is something the carryover. Oh yeah, it's just remainder. No, it's not, because remainder gives you a fractional component. Modulo is integer only. Okay. All right. And I think I've broken your brain enough. And I got another class coming right in after this one. So next week, adder 4 bits, and we're going to play with it. And we'll see what we need to do to create an adder. Okay.
And then what general thing are we doing for Thursday?
Thursday is going to be hands-on-ish. Like we'll compile a program with symbol tables and bring it up in the debugger.
All right.
So the theory will be on Tuesdays, and the hands-on stuff you should know when you leave this place. Like you may not know assembler, but if you know how to use the debugger, that's a win, because every programming language has a debugger. How do you use it? What do I look at? How do I inspect things? Okay. On that note, did the sign-in sheet go around? All right. Great.
Can I try to set up the magnifier? I think the problem was it was on full screen mode and you're supposed to drag it.
Yeah, I don't know how it would do when I record. So let me.
Because I know you're in live mode or whatever.
Yeah, let me just